proposition. We define this language Ln, which is the set of all strings over the binary alphabet for which the nth character from the end of the string is 1, okay? And n is fixed here. N is some given constant, right? Then we showed that Ln is regular because we gave a DFA which accepts Ln. But the proposition asserts something very strong. It says any DFA recognizing, and by the way, recognizing is another word for accepting, Ln must have at least 2 to the power n states, right? So that example doesn't show anything. Our example did indeed have more than at least 2 to the power n states, but it doesn't show anything because this proposition is about any DFA, right? And saying that, oh, we need to remember the last n bits, and to remember n bits, we need 2 to the n states. That is not a proof. That is just an intuition. Okay? So we have to give a proof, and this is how it is done. So in this case, the thing that works is a proof by contradiction. So assume that there is a DFA M with less than 2 to the power n states that accepts Ln, right? Then we know that the number of strings of length is 2 to the power n, and therefore there must be 2 distinct strings. W0, W1, where they are not equal. That's what is meant by distinct, of length n, such that delta Q0, W0 is the Q0, 1. And here, when we write delta, we mean delta hat, of course, because W0 and W1 are strings, right? So we really mean delta hat, but we are, as we said, we are going to overload that symbol without even mentioning it, right? Why is this the case? Because if for every 2 distinct strings, we had distinct target states or ending states, then there would be 2 to the power n states. And by assumption, we have less than 2 to the power n states, okay? So this is a simple application of the pigeonhole principle, right? Because there are 2 to the power n strings and we have less than 2 to the power n states, at least 2 different strings will take us to the same state, right? And let W0 and W1 be 2 such strings. And for that, let I be the first position, starting from the left, of course, where W0 and W1 differ. Because these 2 strings are unequal, I mean, they're of the same length, but they're not the same string. So they must have at least in some position, they must have two different bits. And let the first such position from the left be I. And without loss of generality, we can assume that W0 has 0 in the ith position, and W1 has 1. Because if this is not the case, then we can just switch W0 and W1. So what do we have? We have W0 equals some I minus 1 bits followed by a 0, and then some n minus I bits, whereas W1 equals, please switch off your mic, all of you. This is 1, right? Yeah. So this is the ith position. And there are n minus, because these two strings are of length n, there are n minus I bits here, right? Have I got it right? Okay. So what I'm going to do is append something at the end of both these strings. Okay, so that one of them belongs to ln and the other does not belong to ln. Okay, remember ln is the set of strings that have 1 in the nth character from the end, or the nth bit from the end, right? So I have n minus I bits after the 0 and after this 1. So if I append I minus 1 zeros, let me do that. If I do that, right, what do I get? I have n minus I bits here, and then another what I have here is I minus 1 zeros, right? So in these two modified strings, this particular string does not belong to ln, and this particular string belongs to ln. Do you see that? Do you have any doubts about that? because in the first one, the one at the top, the nth bit from the right has a 0, so it doesn't belong to Ln. Whereas the one at the bottom has a 1 in the nth bit from the right. Okay. Oh, by the way, maybe I didn't explain this notation. So when I write 0 to the power I minus 1, I mean I minus 1 zeros. I have defined this for languages. I've defined L to the n, L to the power n, but we can apply it for strings and symbols as well, right? So does anyone have any questions about this? Any questions? If not, the way we are going to arrive at a contradiction is to show that our machine, the one that accepts ln and which has less than 2 to the power n states, will reach the same state on processing these two strings, the one at the top and the one at the bottom. Why is that the case? Well, because we know that after processing the part, after processing this part, that is the original strings W0 and W1, the machine reaches the same state. I mean, that's by assumption. There must be two strings which are distinct such that delta hat Q0 W0 is delta hat Q0 W1, which means that the machine reaches the same state after processing W0 and W1. So whatever state it reaches at this point, the remaining part of the two strings are same. It's just a string of I minus 1 zeros. Therefore, at the end, the machine will reach the same state, whether it processes the top string or the bottom string. And that is a contradiction because one of these strings is an ln, the other is not. Okay. So the common state, which the same state which is reached, cannot be both final and non-final at the same time. Okay. So to formalize that, so this is the gist of the argument. Just to formalize that, what do we have? We have W0 0 to the I minus 1 does not belong to Ln, and W1 0 to the power I minus 1 does belong to Ln. And we also have delta Q0 W0 is delta Q0 W1. Okay. Now, it is a fact that delta Q UV, where UV are strings, is the same as delta QU, comma V. Okay. So what this is saying is processing the string UV is the same as processing U first and then starting at the resulting state, processing V. Okay. How do you show this? By induction. It's a very easy proof. It follows from the definitions of delta and delta hat. By induction on the length of V, you can show this. Okay. But intuitively, it's obvious, right? And many of these obvious facts we will not bother to prove. But at the same time, you should know how to prove them. Okay? You should take nothing for granted. You can take things for granted when you are experienced, but not at this stage. You should know. Well, you should never take things for granted. You should always know how to prove even these simple things. Okay, we are not going to prove this, but we are going to use this because from here we know that delta Q0 W0 0 I minus I minus 1. By using this fact, we just break up the string into those two parts. We called U and V. So we process W0 first, and then 0 to the power I minus 1. And this is the same as, by assumption, this part is the same as Q0, W1. And of course, the rest of it is the same. And this is, again, by using the fact. And this is a contradiction. Why? Since the left-hand side does not belong to Ln, and the right-hand side belongs to Ln. And the same state cannot both belong to Ln and not belong, belongs to F, where F is the set of final states. Where F is the set of final states. Okay, so that's the end of the proof. Any doubts? Any doubts about the proof anywhere? Okay, so this is how proofs work. We don't rely on our intuition to justify anything. Everything should follow from the definitions using the usual rules of logical deduction and mathematical reasoning. Okay, your intuition may be a guide, but you cannot substitute intuition for a proof. A proof is a proof. Okay, I guess you have no questions on that. So let us proceed to the next important concept, which is non-determinism. By the way, the singular form is automaton. And the plural form is automaton. Okay, so we should not mix the two. Right. So what is non-determinism? It's an extremely important concept in automata theory and theory of computation and theoretical computer science in general. There's no getting away from non-determinism. Unfortunately, many people fail to understand what it actually means. Although they understand the examples and probably know the definitions, but often they are, when they come across proofs, they are at a loss. Okay. So anyway, we'll spend sufficient time to understand this concept. So what is the difference between a deterministic automaton and a non-deterministic automaton? Well, the difference here is given a state, and an input symbol, there are several possibilities for the next state. Okay. And several actually includes none. For some cases, there may not be any next state at all. For some cases, there may be just a single next state. And for other cases, there may be multiple choice of the next state. Okay, so that is what we mean by non-determinism. Okay, so you can think of non-determinism in two ways. Okay, and this is the intuition. One is you can think of the automaton forks or branches into different runs or computations on the same input string. The word run means the sequence of states visited by the machine in processing the input string. So you can give a formal definition of that. I'm not doing that. You can imagine what that definition is. So you can think of the automata branching into different runs. So there are on the same input string, there are different runs of the automaton. Okay. Whereas for a deterministic automaton, there is given a string, there is a unique run. There is a unique sequence of states it will go through. But for a non-deterministic automaton, because there is a choice of next state, there may be several runs of the automaton on the same string, or there may not be any run at all. That's also possible. Okay. So it's as if the computation branches into different runs, and the automaton accepts if any one of those branches is an accepting branch, meaning at the end you reach a final state. As long as one of those branches reaches a final state, the automaton accepts. That's one way to think of it. The other way to think of it is the automaton guesses the right next state which will lead to the input being accepted. And this is the point which most people have difficulty understanding. And I'll try to explain this, because often when talking about Turing machines, we say the Turing machine guesses some number, and then checks whether that number satisfies some property. So what do we mean by a guess? It means the same thing as point number one. Okay? So there are all kinds of choices. As long as one of those choices or sequence of choices leads to acceptance, the input string is accepted. Okay. Another way of putting that is to say that the automaton just guesses the right next state which will lead to acceptance. We'll see an example, and here it is. We saw this before. L is the sequence, the set of all strings containing zero, zero, one as a substring. And we have seen a DFA for that. Here's an NFA. What is an NFA? A non-deterministic finite automaton. So here's an NFA. Right? This is very simple. Often writing an NFA is much simpler than writing a DFA. It has just these four states which we saw earlier, right? So can anyone say why this is an NFA and not a DFA?
At Q0, there are two zeros which are going out.
Yeah. Yes. So at Q0, right? Uh, on a zero, you can either remain in Q0 or you can go to Q1. Okay. So there is a choice. And here is the guess. At some point, you can put it this way. You can, of course, think of a whole tree of branching computations. That's one way to think of it. That's point one. For a given string, there is a whole tree of computations. And as long as one root to leaf run reaches an accepting state, that string is accepted. That's one way to think of it. The other way to think of it is to say, and this is, you'll often find this language in books because this is very convenient. At some point, the automaton, when it sees a zero, the automaton guesses that this particular zero will be followed by another zero and then a one. So instead of remaining in the same state, it moves from Q0 to Q1 and Q1 to Q2 later and Q2 to Q3, okay? What happens if it makes a wrong guess? Well, that computation just dies out. But the way we define an NFA is as long as there is a correct guess, which leads to acceptance, the language is accepted, which is clearly the case here, right? So if any string W indeed contains the pattern 001, at least one computation or run of this automaton on that string will lead to acceptance, right? And there are many computations which will not lead to acceptance. Some will indeed die out because there is no choice of next state for the given string, right? For example, if we get this string, let's take a string such as 0, 0, 1, 0, 0, 1. Sorry. One possible run of this automaton is you start in Q0, of course. Then on a 1, you remain in Q0. There's no choice there. And then you see a 0. You have a choice. You can remain in Q0 or you can go to Q1. Suppose you decide to remain in Q0. So this is one run. And so this is on 1. And this is 0. Suppose you remain in Q0. And then you see a 0. And this time you decide to move to Q1. And then you see a 1. But there is no choice of next state. So this is not possible. In a DFA, for every state and every symbol, you must have a unique next state. But for an NFA, there's a set of possible next states, and that set for a given current state input symbol, that possible set a set of next states could be empty, as is the case here, because from Q1, there's no transition on a 1. So this computation just dies out, right? Even before reading the entire string. But that's okay. And it dies out even though the string is in the language. I mean, this string is very much in L. Right? But we know that there is a correct choice which will lead to acceptance. So that is what we mean by acceptance in the case of NFA. And it makes the concept of non-determinism here, it makes writing automata much easier. As you can see in this case, it's, of course, the deterministic one was not all that difficult, but still it is more complicated than this one. Okay, we'll come to formal definitions. So an NFA, or non-deterministic finite automaton, I'll not write the entire thing, N has the following components. Everything appears to be the same so finite set of states, alphabet, it is delta which is different, because now for a given state and input symbol, you have a choice of next states. So this is a function to the power set of Q. Set of all subsets of Q. And F, of course, is the set of final or accepting states. And as usual, we extend delta to delta hat. But now it'll be Q cross sigma star to 2 to the power Q, the power set of Q, as follows. Again, by induction, delta hat Q epsilon is the singleton set containing Q. Okay. So you should be careful here. This is a set. Earlier, we had just a state, but this is a set of states. And delta hat Q UA. Okay. Here U is a string in sigma star, and A is a symbol following our convention, right? So what is that? Well, we first apply well, let me write it down first and do the explanation later. So this is a set, right? So how do we define this set? We define it as the union of delta R A, where R ranges over all the states that are reachable from Q on reading the input string U. Okay. So this is an inductive definition. To define delta hat on the string UA, you use the value of delta hat on the string U for a given Q. So this is a set. This delta hat QU is a set. So for all R belonging to that set, you compute delta RA, right? And then, which is also a set, and then take the union of all those sets. Does anyone, so let me also write it in an alternative way. You can think of the set of all states P such that, let me write it slightly differently, such that P belongs to delta RA for some R in delta hat QU. So is this definition clear or not? Effectively, what we are doing is to find out the set of all states we can reach on reading the input string UA. We first compute the set of strings we can reach by reading the input string U. So that is a set of states. And for each of those states R, we compute delta RA, and then take the union as R ranges over all the elements in the set of states reachable after reading U. Any doubts or questions? For example, if we go back to the example here, what is delta hat Q0? Zero. This is the set of states which are reachable on reading a zero, right? So you can reach both Q0 and you can reach Q0 or you can reach Q1. In fact, this comes from the definition of delta itself. Maybe I should shift it a little bit to the left. So delta hat Q0, 0 is Q0, Q1. What is delta hat Q0 0, 0, 1? Anyone? So again, it's a set, right? So what are the elements of the set?
Q0 and Q3.
Right. On the other hand, if you compute delta hat Q1, 1, right? That is the empty set, right? Similarly, delta hat Q2, 0, that's the empty set. Yeah? Because there are no transitions labeled 1 out of Q1, okay? Which means that on reading a 1 from Q1, there is no possible next state, right? So we defined delta hat. Now we have to define how to accept a language, right? And that is, and from now on, we'll again drop that hat. We say that Nfa M accepts W if delta hat Q naught W. So this is a set of states. If this set of states contains a final state, then W is accepted. So the way to write it mathematically is this. And the language of M the language accepted by M or recognized by M yeah. Any doubts about this definition? This is the language accepted or recognized by Nfa M. Any doubts about this? Well, using this definition, pattern recognition is very simple, right? If you want an NFA to recognize all you do is, as we have seen, write the first symbol of S, second symbol, and so on, right up to the last symbol. Say S, the substring S is S1, S2, Sn, where each of these Si is just a symbol in sigma, right? So this is what it is. I write sigma here to mean that, you know, there is a transition for each symbol in sigma, and similarly, the initial state. So at some point, the automaton just guesses when it sees at S0 that this is the beginning of the pattern, and I'll go through this. And if you have studied the Knuth-Moritz-Pratt algorithm for string matching, have you studied the algorithm?
No, sir.
In data structures?
No.
No. Okay. So it uses this NFA and converts it to a DFA in an efficient way. So there is another algorithm called the Boyer-Moore. So I guess you didn't study that either. So these are two well-known pattern matching algorithms, text matching, right? Where this notion of where this idea is used. Okay, so let me stop there. Before I go, on Monday, next Monday, what is the date? 30 minus 2 is 11 plus 7, 18, right? And you'll get, it'll be during the class, so there'll be no class. You'll get 30 plus 5 minutes. 5 minutes are meant for submission. Okay? So 9:15 to 9:50. Because when uploading your answers to MS Forms, right, you may face problems. So I'm giving you 5 minutes. You should try to finish within half an hour and try to upload as soon as possible. If things fail, you must send a mail at once with the answers. I'm sure you are used to all this for the last semester. And you should send the mail to the TAs and put me in CC if uploading fails, but immediately. And the syllabus will be everything covered so far, right? Okay, so let me stop there. I'll send you more details about the link and all that. I'll send the details by email. Okay, so let me stop there.